In this video, we're going to talk about Euclidean space, locally Euclidean space, and manifolds at the very end. So let's start off with Euclidean space. We're going to fix a positive integer n. Then Rn is called the Euclidean space of dimension n. When n equals 1, just think about the real line, so that would be R1. When n equals 2, think about the plane, so there's R2. And when n equals 3, think about a three-dimensional space. And so I've tried to draw you the best three-dimensional picture in a two-dimensional world here on my iPad that I could. Now, the Euclidean metric is used to measure the distance between two vectors, x and y. I'm using vectors interchangeably with points here. And to give you some, I have to give you the formula first. So the distance between two vectors is going to be, well, the difference in the components of the vectors. You square that, you add up all those differences, and then you take the square root at the end. So in the n equals 1 case, the distance between x and y, when you do that formula down there, you really are just taking the square root of x minus y quantity squared, so you just get absolute value of x minus y. In n equals 2 on the plane, when you look at the distance formula, it is just the difference in the first coordinates subtracted and squared, plus the difference in the second coordinates, those are subtracted and squared, and then you add those up and take the square root. And then the last thing, over in space, you just do it again. You just have a third coordinate to keep track of. So you notice I've just got an x3 and a y3, because each of my points, x, y, they each have a third coordinate. So I hope that it makes sense in the more general notation down below. I'm saying you just keep repeating that pattern, where you take the difference in the coordinates, square them, add them up, take the square root. Now, what does the metric do for us? It allows us to construct subsets of Rn that are called open balls. And so the notation that I'm going to use in a moment for an open ball is the following. It's B with parentheses, and it's got like two inputs, but I'm using a semicolon to separate the inputs. The first input is the center of the ball, so that's the vector x, and the second input is a radius, that's epsilon, and that's going to be a positive real number. But the definition of the ball here is it's going to be all other points y in Rn whose distance from x is less than epsilon. So I want to look at some pictures of some open balls, and in each of my pictures I'm going to be centered at the origin. So when n equals 1, I'm on the real line and my point is 0. So if I looked at the ball centered at 0 of radius epsilon, well, that looks an awful lot like an interval, and that's because it is. So the ball centered at 0 of radius epsilon is just going to be the interval from minus epsilon to epsilon. If I look at the plane and n equals 2, if I look at a ball of radius epsilon centered at the origin, I'm using the vector notation for 0 there to denote the point 0, 0. Anyway, though, what do you get? It looks like you just get the inside of that circle of radius epsilon. And so that's exactly what I'm going to say here. The ball centered at 0 of radius epsilon, it consists of all points x1, x2 that satisfy that inequality, x1 squared plus x2 squared is less than epsilon squared. So those would be all points, again, inside of that circle. And the last one that I want to look at in space here, in this case, this sphere is going to be what I'll call a ball of radius epsilon centered at 0, 0, 0. That would be all the points satisfying x1 squared plus x2 squared plus x3 squared is less than epsilon squared. So you notice that that white point, if it's inside the sphere, that means it satisfies that inequality down below. So what are the open balls used for? You might have heard them described as being special in some way, or distinguished is a word that you might see in different topology books. And they're useful for generating a topology on Rn. And how do they do that? Well, we're going to call the topology they generate the usual topology on Rn. And let me tell you about how they do it. If fancy U denotes this usual topology on Rn, then if you've got just any subset, that's my regular U of Rn, we're going to say that U is in the topology, so U is in fancy U. That means that U is the union of some, perhaps arbitrarily many, open balls. So the open balls are the building blocks of anything that I'm going to just call open. And remember, the topology is my rhyme and reason for how I'm going to call any subset of Rn open. So the balls are the building blocks. And by the way, just one weird kind of set theory thing, the empty set would be in the topology because it is the union over an empty indexing set. And so if you take a union over an empty indexing set, you get the empty set. So it still fits. All right, so now let's let xt be any topological space. So not necessarily Rn with the usual topology. Our first definition we're going to look at, let's take a point P in X. We're going to say that n, if if n's a subset of x, we're going to say that it's a neighborhood of P if both 1, P is an element of n, and 2, n contains an open set that contains P. So let's look at an example to try to illustrate what a neighborhood is according to this definition. So let's let x be the real line. Let's let t be the usual topology. So think about the building blocks are just open intervals from a to b, like parentheses on both sides. And let's think about the subset n here from -1 to 2, where I'm including -1 on the left, but I'm not including 2 on the right. Then we can see that this set n is a neighborhood of the point 0, because let's just check 1 and 2 above. So just check the definition. That's what you should always do when you're reading through your book. When you do these examples, make sure that all the points in the definition are checked off. So anyway, 1, well, 0 is definitely inside this interval from -1 to 2. I've got a picture for you there, just to help you visualize it. And the other thing I need to check is little Roman numerals 2. Well, you just need to find me some open set that contains 0 and is contained inside of your interval there. So if I'm thinking, I'm looking at that green interval, can I just draw some nice open set that contains 0 and still fits in the green? And there's lots of options. So I'm just going to pick a convenient one, like -1 to 1. That's going to be open. And I see that 0 is in it, and that that interval -1 to 1 is contained in -1 to 2. And just to try to highlight that there, I just drew it up there with red highlighting. So that would be you saying that n is a neighborhood of P. So notice here that like n itself is not open, right? That's okay. So some books don't require neighborhoods themselves to be open. Some books do because it makes things a little bit easier going forward. But n here is not going to be a neighborhood of P equals -1 because there is no nice open interval from A to B that contains -1 that's also contained in n, right? If you think about it, that's because -1, if -1 is in some interval from A to B, then that says that A is definitely to the left of -1. Well, there's no way then that that interval could be inside of n, since the farthest left that n goes is -1. So A is not an n. All right, so a little note here, just to recap what I said. The definition I just gave you of a neighborhood did not require n to be open. Some books do. So in particular, a very popular book is like Lee's book on topological manifolds and smooth manifolds. That goes ahead and just says, if you hear the word neighborhood, you can assume that it's open. So just pay attention to what you're reading though. Our next definition we're going to look at, if xt is a topological space, we're going to say that xt is locally Euclidean of dimension n if each point in x has a neighborhood that is homeomorphic to Rn. I've made lots of videos recently about homeomorphisms. You should go check those out if you don't feel too comfortable with that concept. But what do we want to think about here? What is this trying to get at? You can think of Rn as sort of flat space. Now, topological space X need not be flat. So think about like a sphere in its own right. So like, don't think about embedding a sphere in space, right? Don't think about coordinates or anything like that. Just think about a sphere. And so it's not flat space. So if we're going to say that X is locally Euclidean, that means that at each point in X, we should be able to kind of zoom in so that X looks flat near P. And you've seen this idea before in calculus. You know that the tangent line to a curve y equals f of x at P approximates f at P. And the idea there is if I zoom in, the yellow line looks an awful lot like the green line when you're near P. And you also saw it in Calc 3. The tangent plane to a surface z equals f of xy at P. It approximates f at P in much the same way. If you were to zoom in on that point on the surface, you can hardly distinguish between the surface that's green and the tangent plane that's yellow. Our last definition here is going to say that a topological space is a manifold of dimension n if three things happen. One, it's locally Euclidean of dimension n, so that means that each point should have a neighborhood that looks just like Rn. Number two, it's Hausdorff. That means that any 2 points should have open sets that are non-empty, that separate them. And number three, that it's second countable. So the basis that you take for the topology, you can find a countable basis for the topology.